Welcome back to this next video in which we are discussing finite dimensional vector spaces. Okay, so we're currently in the process of proving that if we have a linearly independent set of vectors, v1, v2, all the way up to vn, and a set of vectors which spans the entire vector space, v1 bar, v2 bar, all the way up to vn bar, that the order of the linearly independent set of vectors is less than or equal to the order of the set of vectors which spans the entire vector space. Okay? Right, so the way we're trying to prove that is by assuming the exact opposite. Okay, so we're going to assume that little m, which is the number of vectors in the spanning set, is strictly less than the number of vectors in the linearly independent set, or rather, the number of vectors little n in the linearly independent set is strictly greater than the number of vectors in the spanning set. Okay, so we're going to assume the exact opposite of what we want to prove, and then we're going to arrive at a contradiction. And the contradiction we're going to arrive at is that this set L isn't actually linearly independent at all. Okay, now how can we prove that it's not linearly independent? Well, to prove it's not linearly independent, we need to prove that there is some linear combination of the vectors v1, v2, all the way up to vn, which is not the trivial linear combination which gives the zero vector. Okay, so we need to find C1, C2, all the way up to Cn such that this is going to be true. Okay, now what's our approach to actually find C1, C2, all the way up to Cn? Well, our approach is write all of the vectors in the linearly independent set, so the unbarred vectors, in terms of linear combinations of the barred vectors, which are the vectors from the spanning set, capital S. Okay, so because this set spans the entire vector space, I can write each vector from the linearly independent set as a linear combination of the barred vectors, which is what I've done here. Okay, then what I've done in this condition, I have substituted in v1 is equal to this, v2 is equal to this, etc, etc. Okay, and what you end up with is, after a bit of manipulation, this expression here. Okay, so you have a linear combination in the barred vectors v bar 1, v bar 2, all the way up to v bar m, which we want to equal the zero vector. Okay, now, we don't know that the barred vectors are linearly independent, so we don't know that the only way of getting a linear combination of the barred vectors to equal the zero vector is for it to be the trivial combination. However, the trivial linear combination is always a solution, basically. It's always a way of getting a linear combination of the barred vectors to actually equal the zero vector, and it's the only one that we have even the faintest idea about. Okay, so if we insist that these horrendously complicated coefficients that are in front of the barred vectors, which are elements of the field, are actually all equal to zero in the field, then of course it will be satisfied that this structure will actually equal the zero vector, that this linear combination of v bar 1, v bar 2, all the way up to v bar m will equal the zero vector. Okay, so if we can pick C1, C2, all the way up to Cn cleverly enough, such that all of these coefficients are actually equal to zero in the field, okay, i.e. this system of linear equations needs to be true, then we'll be in business. Then that arrangement, that combination of C1, C2, all the way up to Cn will actually be a linear combination of the vectors v1, v2, all the way up to vn, which gives the zero vector. Okay, so we're now interested in solving this system of linear equations. Okay, so we've got a system of linear homogeneous equations which make complete sense in the field, and that's an important point to note. Everything here now is about the field, okay? The vector space is gone. This is a system of linear equations in the field. All of the multiplications and the additions here are in the field. The zeros are zero in the field. Okay, so what we are looking for is C1, C2, all the way up to Cn, such that this combination of elements of the field satisfies all m of these equations. Okay? Now, one obvious solution to this is that if all of them were equal to 0 in the field, so if C1 was equal to 0 in the field, C2 was equal to 0 in the field, all the way up to Cn equaling 0 in the field, because 0 in the field will multiply by any other element of the field to give 0 back again, and when you add lots of zeros together you end up with 0 again. Okay, so that is a solution to this, but of course that corresponds to the trivial linear combination of our vectors v1, v2, all the way up to vn. We need a non-trivial combination of those vectors, so we need a non-trivial solution to this system of linear homogeneous equations. We need solutions where not all of these CI's are actually equal to 0 in the field. Okay, and we can always find that. The reason being that we have m equations here, okay, in n unknowns. The unknowns, remember, are the c's, so we have n unknowns and m equations, and remember n by assumption was bigger than m. Okay, so we have more unknowns than we have equations, and whenever you have more unknowns than you have equations, you can always find a non-trivial solution, and this is true in any field. Okay, so that means that we can find a non-trivial solution. We can find C1, C2, all the way up to Cn, which is a non-trivial solution to this system of linear homogeneous equations, and therefore those C's will work as a linear combination of my vectors v1, v2, all the way up to vn, which will give the 0 vector, and hence I've disproven this set being linearly independent, arrived at a contradiction, and therefore my assumption must have been wrong. Therefore we can say that n must be less than or equal to m if it's not strictly greater than n. Okay, so end of proof. However, I do just want to investigate more why it is the case that you can always find non-trivial solutions to a system of m equations in n unknowns, which are all linear homogeneous equations. Okay, so the reason is, and how we're going to pursue this, is that Gaussian elimination works. Okay, now hopefully you will have seen Gaussian elimination before in the context of solving linear homogeneous equations in the real numbers. Okay, but actually Gaussian elimination works in any field, okay, which is something you might not fully have appreciated yet. So I want to let you appreciate that now, and we'll discuss why it is true that you can always find a non-trivial solution to this. Okay, so the first thing is just to copy out that system of linear equations onto another piece of paper. Okay, right. What I'm going to do is I'm going to alter them a little bit. I'm just going to alter the way they're displayed. I'm not actually obviously going to alter the equations. I'm not allowed to do that, but I'm just going to alter the way they're displayed. Okay, the first thing I'm going to do is I'm going to put the coefficients in front of the actual variables. That just makes it look a bit more normal. Okay, I can do that because multiplication in the field is commutative, so it doesn't matter what order you actually do it in. The other thing that I'm going to do is I'm actually going to put the little nth term in these equations actually in. And the reason I can do that is because little m is less than little n. Okay, so there is an nth term in all of these m equations. Okay, so I hope that will become more apparent what I mean by that in just a moment. So let me copy these out. So let's firstly do the orange equation. So I'm going to have a11 times c1, so here's my variable, plus a21, and remember the a's are constants, they're just elements of the field, times c2, plus on and on it goes. And now what I'm going to do is add in a term that I wasn't displaying before, but which was always there. It was just in this dot 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 portion before. Okay, so now what we're going to have is a m1 cm, and you will see why I want that to actually be displayed. And then we'll go plus dot 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 all the way up to the final one, which is a n1 cn, like so. And I want this to equal 0. So that is just the orange equation rewritten, basically, okay, in a way that's going to be more useful to me. Okay, now I'm going to do the same thing for the green equation and the red equation. Okay, so a12 c1 plus a22 c2 plus all the way up until we get to a m2 cm, like so, plus dot 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 all the way up to a n2 cn is equal to 0. So there is our green equation, so I'll once again underline that in green here. And then we'll go all the way up to the nth equation, so I'll put this here, so we'll have A1m this time times C1 plus A2m times C2 plus all the way up until we get to AMM Cm, and then we'll go all the way on until we get to ANM Cn, like so, and that will also equal 0, and I'll underline that equation in red. Okay, so there is my system of linear equations just moved onto this page. Okay, so now I want to explain how Gaussian elimination works in an arbitrary field. Okay, so I'm just going to give these names firstly. So this is equation number 1, this is equation number 2, and we'll call this equation number m here. I'll just colour in their numbers as well. So equation number 1 can be in orange, equation number 2 is here in green, and equation number m is in red here. Okay, so let me just make sure everyone understands what we are trying to do here. We are trying to find elements of the field C1, C2, all the way up to Cn, such that all of these equations are satisfied by that combination of elements of the field. Okay, and what we're trying to show is that there is a non-trivial solution to that, i.e. we know that there is the one where all of these are equal to 0. I would like a more interesting one. Okay, so what I'm about to show you is Gaussian elimination, okay, which is a way of solving systems of linear homogeneous equations like this. Okay, so if this thing here is true, okay, so if equation 1 is true, okay, so if any solution C1, C2, all the way up to Cn is going to satisfy equation 1, then it is always true that I can write C1 as a linear expression of the rest, basically. I can write it as a linear expression involving C2, C3, all the way up to Cn. Okay, and let me explain the reason for that. So what I can quite simply do is take all the things that I've got here onto the other side. Okay, so let me firstly do this, okay, and this is, remember, all algebra in the field. Everything we're doing now is in the field. Okay, so what I'm going to do is keep my A11 times C1 on this side, and then what I'm going to do is take all of the other terms onto the other side. So what I'm going to get is A11 times C1 is equal to the additive inverse of A21 times C2 plus the additive inverse of, and then we'll have A31 times C3, and then it will go on and on all the way up until, and I won't bother putting the nth one in, we'll end up with the additive inverse of AN1 times Cn. So that's perfectly valid. If equation 1 is true, I can quite simply do that. Okay, this equation is also going to be true. Okay, now remember from basic field algebra that when you have the additive inverse of an element in the field, okay, that is the same as -1, the additive inverse of the multiplicative identity in the field, times that element of the field. Okay, so this is just equal to -1 times all of those things. Okay, so we've got -1, and I'll just sort of squeeze this in. I might actually write this in. So we've got -1 times A21 C2 plus -1 times A31 C3 plus all the way up until we'll end up with -1 times AN1 Cn, like so. Then, because of associativity of multiplication in the field, what I can do is rearrange the brackets here. So at the moment, I've got the brackets around this thing times this thing. And then I'm saying, after you've done that, then multiply it by -1. What I'm going to do is reassociate this, and I can do this because field multiplication obeys commutativity. Okay, so I'm going to reassociate it so that it's -1 times A21, and then times C2, and so on for the rest of these. So I have -1 times A31 times C3, plus on, and we'll end up with -1 times AN1 times Cn. But of course, when we multiply any element of the field, which all of these are, by -1, we just end up with the additive inverse of this. So this is just equal to -A21, -A31, -AN1, like so. Okay, so I've just modified my equation like so. Okay, and that's all perfectly valid field operations there. So now basically I have this written as a linear expression of all the others, C2, C3, Cn, just some element of the field multiplied by all of them. Okay, then what I'm going to do is I'm going to multiply both sides by the multiplicative inverse of A11. Okay, so what I'm going to do is multiply by the multiplicative inverse of A11. Now, of course, this does assume that we have a non-zero coefficient A11. Okay, if it's not a non-zero coefficient there, then just move up the equations basically. Okay, so you'll need one of them at least to have a non-zero coefficient. If they all have zero coefficients of C1, then of course C1 doesn't participate at all. Okay, so what you'll have to do then is bring one up to the top that does indeed actually have a non-zero coefficient. So I'm going to assume that my equation 1 is one of the ones that does have a non-zero coefficient, so that I can actually multiply by the multiplicative inverse of A11. Okay, so I'll multiply both sides by the multiplicative inverse of A11, like so. Okay, and when I do this on the left-hand side here, of course, I can reassociate. So I'll put the brackets around 1 over A11 times A11. Okay, and of course that will give me the multiplicative identity of the field, so this side will just end up as C1 intuitively, as it should do. And then on the other side, what I'll end up with is 1 over A11 times negative A21 C2 plus negative A31 times C3 plus on and on, all the way until we end up with negative AN1 times Cn, like so. Okay, then what we can do is apply distributivity of multiplication over addition and expand out this bracket here. Okay, then after we've done that, and I'm going to do two steps in one here, once we've expanded out that bracket, we will then want to reassociate the multiplication, because what we'll end up with is this thing multiplied by this thing and then multiplied by this thing, but I want it to be this thing multiplied with this thing and then multiplied by that thing. Okay, so what we'll end up with here is 1 over A11 times negative A21 times C2 plus 1 over A11 times negative A31 times C3 plus all the way up until we have 1 over A11 times negative AN1 times Cn, like so. And there, what I have done successfully now is write C1 as a expression, a linear expression in the others, C2, C3, all the way up to Cn. Okay, so what I'm now going to use that to do is I'm going to substitute in C1 is equal to this in all the others. Okay, because any solution to this system of equations, it must be true that C1 is equal to this, otherwise the solution wouldn't satisfy equation number 1. Okay, so what I can quite simply do is then stick in for C1 this expression, okay, which is a linear expression in all the rest. Okay, and that will get rid of this first expression from all of the other equations. So what I'm going to do is get rid of that from all the other equations. Okay, and it will then change the bits that I have of the remaining terms. So it will add lots of bits on to all the remaining terms here. Okay, but it means that now I can change this system of linear equations so that only the top one actually has a C1 term and all the others have a 0 C1 term. Okay, so they've got rid of that C1 term from all the others. Right, so that's the basic principle of Gaussian elimination, and now what we're going to do is continue it on. So now what we've got is we've got one equation up here, equation number 1, which is a full length one, and now all the other equations have lost this C1 term. They no longer have that C1 term. Now what you're going to do is the same thing for the second C2 term using equation number 2. So you're going to use equation number 2 here to now write C2 as a linear combination, or I shouldn't say linear combination, a linear expression involving all the remaining ones, C3, C4, all the way up to Cn. Okay, but of course not C1 because it doesn't have any C1 anymore. Okay. And then what you will do is substitute that into all the other equations, including equation number 1 here, and get rid of the C2, and it will just change the all the remaining terms, so C3 all the way up to Cn. So I'm going to cross that one off from here, and we'll continue on down. You'll cross all of these off right the way down to the nth equation here. Okay, so all the equations bar equation 2 have now lost the second term. Okay, and you continue on. You then go to equation number 3, and you say, okay, I'm going to use equation 3 to write C3 as a linear expression involving C4, C5, all the way up to Cn. Okay, and I'm going to use it to get rid of the third expression, or the third term, from all the other equations. So equation number 1 will lose it, equation number 2 will lose it, equation number 3 will keep it, but all the remaining equations will lose it as well. Okay, and you continue this process on right the way down until you get to the nth equation, and you have then lost all of the previous terms. Okay, so the nth equation no longer has a first, second, or an m minus 1th term. It has all the terms on from that, so m, m plus 1, all the way up to n. Okay, and what you will then do is you'll use this to write Cn as a linear expression in the C's that are above m, okay, and then you'll use this to remove the nth term from all the other equations except the nth one. So only the nth one will actually remain with that nth term. Okay, so what you effectively do is rewrite the equations in this new way, where for the initial m by m square here, so you've got effectively a square here, okay, and I'll highlight this square up here. So I'll just get my yellow pen here. Okay, so we've got a square effectively here. Okay, and in that square, it's a very, very simple square, because equation number 1 only has a first expression. It doesn't have any of these all the way up to the nth term here. All of those bits have gone now, and then it does have the bits after that. Okay, so these other bits are still remaining. So m plus 1 all the way up to n, those bits are still remaining. Equation number 2, the only bit that it has is this second bit. All the other bits, number 1, and then all the bits following number 2 up to number m, have been removed from it, and then of course it has the tail over here as well. Okay, and this goes on. So we just have the diagonal terms here. Those are the only terms that are actually going to be there. Okay, right. So now what do you do? Well, what you can now do is you can let the other C's, so the C's above Cn, you can let them equal whatever you like. Okay, so let Cn plus 1 all the way up to Cn, let them equal whatever elements of the field you like. Choose arbitrary elements of the field, specifically choose non-zero elements of the field, okay, and stick them in there. Okay, now the way that you're going to choose the rest of the C's, C1, C2, all the way up to Cn, is you're going to choose them so that all of these equations are satisfied. So you've chosen these ones, you've set these ones now, and you can stick them into what's the new equation 1, so the modified equation 1. And remember, the coefficients in front of these remaining terms over here that I'm pointing to now, these are going to be very different from the ones in the original equation, because we have continually been substituting in things, and those will be changing the remaining terms here. Okay, so you can now actually just work out what the answer to that actually is, though. So once you've got these values set, just work out what the answer to that is, and then just set C1 to whatever you need to set it equal to make this term balance this term and make the equation true. Okay, equivalently, for equation number 2 here, Cn plus 1 all the way up to Cn, you've chosen those, stick those in, work out this value of the tail portion here, okay, and just make C2 exactly what you need to make it balance this portion, counterbalance this portion, and go on. Okay, and this is the beauty of the diagonal portion, okay, that each equation can just set the corresponding C value basically, so that it counterbalances this tail portion that you've just made up. Okay, so that then is the proof that you can always find a non-trivial solution then to a system of linear homogeneous equations where you have more variables than you actually do equations. Okay, and that technique is called Gaussian elimination. Okay, so that means that we can always find a solution. Bringing back up this picture here, we can always find a solution. I can find C1, C2, all the way up to Cn, such that this system of linear homogeneous equations is satisfied, okay, and which is not a trivial solution. Hence, what I have now worked out then is some values for C1, C2, all the way up to Cn, such that this linear combination of the vectors v1, v2, all the way up to vn will actually equal the zero vector, and this is not the trivial linear combination of those vectors, so that means that these vectors are not linearly independent, but my initial basic problem involved a linearly independent set. I said let this be a linearly independent set of vectors, so that's a contradiction, and therefore this can't be true, so the only other possibility is that n must be less than or equal to n. So we have now proven then that a linearly independent set of vectors will always have a size less than or equal to a set of vectors which spans the entire vector space. Okay, so, but that was just a side theorem. The main theorem that we wanted to prove was that if you have two bases of a vector space, that they have the same number of vectors in them, specifically a finite dimensional vector space, I should say. If you have two bases of a finite dimensional vector space, we want to prove that they have the same order, basically. So we want to prove that the order of B1 will equal the order of B2. So how can we do that using this? Well, it's so beautiful. Okay, B1 is a basis, so it is a linearly independent set of vectors. B2 is a basis, so it spans the entire vector space. So we can now apply this theorem to say that the order of B1 is less than or equal to the order of B2. Okay, so I'll repeat that. A basis, remember, is a set of vectors which spans the entire vector space and which is linearly independent. If B1 is a basis, it's a linearly independent set of vectors. So let it be L in this problem here, okay, in this theorem. If B2 is a basis, then it spans the entire vector space, so let it be S. So we can then say that the order of B1 must be less than or equal to B2. But of course, the exact same argument works in reverse, okay? Because if B2 is a basis, then it is a linearly independent set of vectors, so let it now be L in this theorem. And if B1 is a basis, it spans the entire vector space, so let it be S in this theorem. So we can also get to the equation that the order of B2 is less than or equal to the order of B1. Okay, so the only way that those two conditions there can be true is if they are actually both equal to one another, and hence we have proven that the order of any two bases of a finite dimensional vector space is the same. A basis has to have a fixed number of values in if we're talking about the same vector space. Of course, if you have different vector spaces, they don't have to have the same sized basis. But if we're talking about one vector space and we've got multiple different bases for that vector space, which are just sets of vectors which are linearly independent and span the entire vector space, then they have to have the same number of vectors in, providing this is a finite dimensional vector space. Okay, we're not talking about infinite dimensional vector spaces. That's a topic for analysis, not algebra. Okay, right. Now, one final definition which I'll give you in this video, and then we'll have a break and come back in the next video to prove a final theorem. Okay, the final definition that I want to give you is that this is what we will call the dimension of a vector space. Okay, so the dimension of a vector space, denoted dim v, okay, so this means the dimension of a vector space is a very important constant concerning vector spaces. It's a parameter associated with any vector space that is finite dimensional, and this is just going to be the order of any basis. Okay, so if B is a basis of this finite dimensional vector space, how many vectors does it have in? That's what we will call the dimension of the vector space, and we know now that that's a well-defined parameter because we know all bases that you can possibly dream up for this vector space, capital V, will have the same order. That's what I've just proven. Okay, so if you set this task to two people, you tell them to work out what the dimension of the vector space V is, even if they both use completely different bases, they will get the same answer because all bases have to have the same order, okay, and therefore the dimension of the vector space is well defined. So it's a parameter that we can associate to finite dimensional vector spaces, okay? Right, so we'll have a break there, and in the next video what I will prove is one final theorem, which is that the dimension of a subspace of a vector space is always less than or equal to the dimension of the entire vector space.